Dear ladies and gentlemen, until last year, there was no neutron multiplier that can operate in a fusion reactor blanket. Without neutron multipliers, not enough tritium will be produced in the blanket, which means not enough fuel for the fusion reaction. But now our innovation should solve this problem. I want to tell you about three aspects of our innovation: innovative material, design, and technology, which are closely related and intertwined. Let's start with our innovative material. Beryllium as an element is the best neutron multiplier and it's a ferromoderator at the same time. The beryllium-based breeding blanket is the most compact and can work with lower lithium-6 enrichment. The use of beryllium avoids numerous problems of liquid metals such as corrosion, bubbles formation, and magnetohydrodynamics. In addition, a beryllium blanket can operate at temperatures most suitable for steels as construction materials. At the same time, metallic beryllium reacts strongly with steam and air as shown below. Under neutron irradiation, beryllium swells intensively, forming a very high porosity. Beryllium also retains a lot of tritium on the surfaces of hexagonal-shaped bubbles during irradiation. But the addition of just one titanium atom to 12 beryllium atoms radically changes the structure and properties. This intermetallic compound called titanium berylite has much higher operating temperatures due to better corrosion resistance and due to much less swelling. Under the same irradiation conditions, beryllium looks like Swiss cheese in the left and berylite has almost no porosity in the right. Looking much closer to the material with Tm, we always see large hexagonal bubbles in beryllium and very small ones in berylite. This also leads to significantly lower tritium retention, which is important from a safety point of view. In fact, at working temperatures above 500 degrees, berylite practically does not retain tritium. And such a new material with unique properties anticipates the innovative design of the blanket. Let's take a look at the previous design. This is a sector of DEMA fusion reactor with a blanket module. It has layers of 1 mm beryllium pebbles and lithium ceramics. The beryllium should be shaped like small pebbles to withstand further strong swelling and to facilitate the tritium release. The pebble bed concept was developed in the 90s, but is still not feasible for demo volumes, which requires 300 tons of beryllium pebbles, thousands of machines running continuously for several years and producing pebbles one after another. The switching to a new material, namely titanium berylite, allowed to change the blanket design. Now berylite blocks should replace beryllium pebbles for neutrons multiplication. Due to higher packing factor, this design provides a higher tritium breeding ratio. Everything is fine, but the problem was the lack of technology for the production of such hexagonal blocks from berylites. Thus, innovative design in turn requires innovative technology. Since berylite is a very hard and brittle material comparable to gemstones, its manufacture has faced many challenges. Conventional casting resulted in high porosity and excessive evaporation of beryllium. Powder metallurgy route with extrusion and hot isostatic pressing provided high-quality fine-grained material, but the use of capsules made the technology too expensive and low scalable. And the third way, based on vacuum hot pressing of already synthesized berylite powders, led us to success. A lot of work was done before such a mock-up was obtained. Unfortunately, the technology is scalable and our industrial partner, Ulba Metallurgical Plant, Kazakhstan, manufactured the first of its kind full-sized titanium berylite block in industrial conditions using industrial equipment. Now, by starting this video courtesy of the Ulba, you can see some of the steps in the production of a berylite block using this innovative technology. After cold pressing of already synthesized berylite powder, a graphite mold is filled with it. Then the mold is transported to vacuum hot press here in the left. You see, this is a real plant with huge machines and equipment. Last steps of preparation. Then the chamber is closed and vacuum hot pressing begins. After pressing and fanning machining, a full-size block with 144 mm in diameter and 150 mm in height was obtained. I would like to emphasize that the technology was developed over a short period of 1 year, and Ulba can produce tons of these blocks on demand. Let's take a look at the structure and composition properties of the block obtained. It's a single-phase titanium berylite with traces of other phases. The material has a very low uranium content. It's 500 times less than American beryllium, which means they won't be long-life isotopes after working in a fusion reactor. The obtained berylite has a fairly high density, small grain size. It's a very hard material with a fracture toughness like many ceramics. And one very important point, during the past operation of the fusion reactor, the berylite block will experience rapid heating and cooling. I will start a video, again courtesy of Ulba, in which we mimic the operating conditions of the demo reactor. The berylite mock-up is placed in an induction furnace. It is rapidly heated up to 900 degrees, the video is accelerated, and then cools down to 200 degrees in a compressed atmosphere. Another cycle, the block shines like the sun and turns gray again. More cycles with even more video acceleration and continue up to 50 cycles. As a result, there are no cracks, no strong oxidation after 50 thermal cycles. In the next step, we will test the full-size block, and the preliminary experiments were already successful. Thanks to these outstanding properties, such berylites can be used as high-temperature materials for air and space applications. One more point. We turn to the ITER bosses. Our material must be tested in ITER TBM. Neither beryllium nor lead can work in demo, only berylite at the moment. We believe that the full potential of innovation will be unfolded in demo and further fusion reactors. I do thank you for your attention.